Alright, boys. Just waiting for people to get in here and stuff. I got a little bit of amazing robot updates for you guys. I've been working on the robot a little bit recently and came up with some really powerful inventions and solutions um, for the robot. Really crazy stuff. Totally novel, totally new to me. And I can't wait to share it with you guys. So, alright. So, first, here would be our robot arm bone. Okay. And let's say here's one of our motors. Oh, and by the way, I have a big update on the motors. Remember I've been using for the hands brushed DC motor? Well, I decided I found this cool new robotics forum thing. It's called Robo Waifu. It's a group that is trying to build humanoid robots. Um, and some of them in the group want to have it as like a replacement for a girlfriend. So like a domestic partner situation. Slash sex bot type of thing. But not all of them, but some of the people in the group, that's the point. So that's why they're calling it a waifu. But some of them, it will be like not for sex, but still nice to look at, but it's just a household assistant type of thing. But they'll still call it a waifu because they intend to develop a companionship with it and have it be cute, like um, an anime robot type of design. And some are interested sexually in that, some not. But there's a variety. So, anyways, though though I'm not on board with robot sex because that's sex outside of marriage, in my opinion, that would fall under masturbation. I think I'm not sure that it's fornication or adultery. It's borderline. It's very similar, and God might count it as that. So I wouldn't play around with that personally from a biblical point of view. But um, I still feel that I can participate in that group since they're basically making a household robot companion. It's too similar. Like I can't be too nitpicky since not all of them are doing that for the purpose of sex. And any humanoid robot, somebody will probably want to use it for sex regardless. So that's going to be in the back of everybody's mind anyway. So joining a group that's building humanoid robots, some people are going to have sexual motivations behind that for either the end user client or themselves or whoever. That's going to be in the back of everybody's mind. So I'm not too concerned with that being in the back of people's mind. My personal use will not be that. I won't promote that type of usage of it, but I still join that group to just learn about their progress and share some of my findings. So, anyways, in that group, they were talking about we don't want to use pneumatics because it's too loud, and this is a robot for indoor use in your personal home. You don't want some loud thing. You have to turn it off all the time if it's so loud. So quietness is a huge paramount importance, and just having somebody say that out loud really was good for me to hear. Not out loud, but in the chat room. It really drove home something I already felt, but hadn't realized how important that is until somebody else mentioned that is so important. And I was like, wow. So that's why I got rid of the brush DC motors. I'm going with brushless now. So, anyways, these are the little motors with the little output pulley. Now, for electronics, originally I was planning just to like bolt all the circuits to the side of the motor for the motor, but I've got a way more novel approach now since for brushless motors the circuitry is getting way more complex than just a brushed DC motor, which just requires a little H-bridge chip, the L9110S chip. That's not going to work for brushless. That's going to require 6 MOSFETs in addition to a ton of little SMD components. Each of the MOSFETs needs to be heat sinked and everything. So here's my solution for that. I call this like the lawn lawn method or blades of grass method, all of my electric circuits are going to be like blades of grass. You'll be able to part them with your hands and just spread them out. Like if you look into overgrown grass, you're going to see dandelions, you're going to see flowers, you're going to see tons of blades of grass, but you can get to the ground. You can move them aside and part the grass to see the actual soil beneath and the little ants crawling around and stuff. You can do that. And so I'm thinking, like, from a mechanic's point of view, for working on cars, people hate more than anything having to uninstall parts to be able to get to other parts. So what if you could just move parts to the side if they don't need to be stationary? And that's actually better for breakages. So like if you throw a football at this robot's arm and it hits the arm, if everything like has some flex and some give, maybe nothing will break. So the same for the electronics. If it's all very flexible, it will just move and conform to the shape of the football's tip hitting the arm, rather than all being rigid and then something breaks. Like if you had just a big circuit board, that could just crack in half or something. So although that's pretty strong, but if you want to make everything really fine and tiny and micro size, but still very flexible and Deadbuggy style without a circuit board, because the whole robot is like one giant circuit board. There's going to be like thousands of parts. The robot's arm has 25 motors in it, and that's going to have, each motor requires like, I don't even know, it's going to be like 30 SMD components plus like one microcontroller assigned to every 2 motors. So we're going to have like 12 microcontrollers in the arm. It's going to be insane. All the complexity is just going to be insane. And where do you fit all that? Are you going to put a giant PCB ESC for each motor? Like, where's that going to go? So that doesn't work. So what we're doing is the lawn style. So this will make for a way to part all the electronics away from whatever motor you want to access or whatever thing you want to sew into the robot arm or just fix or whatever. It will be separated. So here's how the lawn works. You can easily move it to the side. You don't have to uninstall anything this way. So it's going to start with like a L-shaped bracket like that, and I think of it kind of like a palm tree, or like by the way, this will be like a 0.01 millimeter nickel strip, which I have here. It's for welding. Where is it? Hold on. What the heck? It's for welding battery tabs. Here we go. Like this. It's flexible, see? So like, if you build the circuit off the top of this, you could just move it out of the way. In like any direction, it will flex. Forward, backwards, like it will torque itself. So anyways, yeah, it will be able to move like different ways. So I could just move, if I have a bunch of these, if you picture like a bunch of these coming off, but I want them like long. I want them like this long. And I'd be able to like work on the circuit as like petals on a dandelion will be like a central point, and then like if you do like a little MOSFET, all the wires going to the MOSFET will lead back to the center and then back out to a microcontroller. And then the microcontroller could be actually the top, like the stamen of it. I thought, just for the cuteness of that, the IC chip would be the stamen of it, and then all the wires will run off the sides of the IC chip, Deadbug style, curl back around, and then come down the stamen. And then the wires will then fork out to each SMD component that you need, like a MOSFET, a little LED light, a reset switch. It could even go out to a little USB plug for the purpose of programming it. It could go out to that. It could go out to a little potentiometer maybe, or that it could travel. The microcontroller, which is up here, could travel down and then down the base, and then off to another little blade of grass that has like a switch on it that could turn on or off all the LEDs in the system. It will also go like to another blade of grass that will have at the tip of that blade of grass a fuse that will handle like 2 dandelions, I'll call them. So like if it's only got one component at the top, I'm going to call it a blade of grass. But if it's got a microcontroller, which will be the stamen, and then a bunch of pedals, which will be all the things going off to a ton of MOSFETs and stuff, then I'll call that a dandelion. Although I also been thinking of it as like a palm tree looking design. But I think it's going to be more like a flower maybe. A flower, dandelion, palm tree, same difference. It's going to have a long stem and then like a flower design for the circuitry. So let me go ahead and draw it now. I kind of been pointing in the air and describing it, but I'll draw it now a little more. So starts off with just this like leg just to get things going, and then let's just say like maybe it should be, no joke, like how tall is that? Maybe like 20 centimeters long. 20 centimeters long will be just the, if we think of the palm tree example, it would be the trunk before you hit the palm tree of all the electronics that are coming off of this. So then we have this thing bent back out again, and on the top of this we can put, and we're actually going to do this, guys, we're actually going to use a 32 pin ATmega 328 PB-AU TQFP form factor 32 pin, those little Arduino chips, not the dip style. It's very important not to use anything big. It has to be as small as possible, delicate, but not delicate. So it's delicate. I say delicate because it's tiny, but it's not delicate because it's attached to strong stuff. This is nickel strip. Nickel strip is very strong. This is much stronger than copper. And actually, I love how it looks on this battery from inside my Milwaukee drill battery pack. I took it apart. Look at how they do their wire connections with a nickel strip. That's a nickel strip. They didn't run a jumper wire. They welded the nickel strip here and then had it make this really nice clean bend. They folded it in the middle like a V shape and ran it up between two batteries. Look how clean. Look at how nice that looks as a wire run. And then it like bends up and in, and then it comes up, and then they solder it into the top of a PCB. So that's their wire run. You don't see like a big ugly connector that has like a jumper cable that then runs and then they like electrical tape it to the side of this thing. No, it's like so clean and neat. It just comes out the bottom of the USB of the PCB and then comes down. This really inspired me to start doing, instead of running all my wiring off of a little USB or a little PCB with jumper wire, I was like, I should use nickel strips because you can weld it with a spot welder to make your joints instead of soldering. That'd be kind of cool, and it's going to be stronger. Um, and you don't have to worry about like when you solder, like these joints I made with jumper cable male to female are kind of big, um, bigger than my preference, and I don't know. It's not horrible, but I just feel like I feel like I should use nickel strips now for everything. I could change my mind later on that. For some stuff, I still might use copper wire, but I want to start using a lot more nickel strip because you can spot weld connections, which I think is faster than soldering. But I could be wrong in that, and I admittedly am kind of a beginner at soldering, so I'm more attracted to trying other things right now. In fact, I've even been experimenting with making silver solder circuitry. So this is on like a little piece of nitrile rubber on some adhesive transfer tape, and you can see I drew a little conductive circuit with the tip of my X-Acto knife, and this all works. I tested it. It takes 24 hours to dry though, that's the only problem. I put little testing points, and this is completely flexible. And these are little pieces of copper tape from a big roll of copper tape that I just cut out by hand to make little copper traces. And the idea is this copper tape, you can stick it on, but then like if you applied heat, it would like peel off. But if you just put silver solder, it doesn't peel away. So, and then you could actually use UV cure solder mask to like glue the copper tape onto the surface way better over the top of it, so it wouldn't peel away even if you did want to apply heat later. So some cool ideas for like other kind of ways to do my circuitry that I'm experimenting with right now. But anyways, back to the blades of grass thing. So we'd have our microcontroller. Okay, first of all, we need to apply UV cure solder mask now to this nickel strip so it's not conductive anywhere near the top. Like probably just paint it on the whole thing, maybe, I don't know. But definitely paint it on anywhere near the top, like anywhere around here. And so now you can actually solder right next to this thing, but none of the solder will stick to it or conduct to it. So now you can actually stick your, well, let me just draw a breakout view of this now. Like this is like a zoomed in view. So we'd have it like this. Okay. So that's this, but bigger. Just okay. It's just as a close-up. And then you put your microcontroller on here, and I think it's like 4. No, it's 8 pin. Oh my goodness, it's so many. Oh wait, is it 8 or 4? 4, 8, 12, 16. Isn't it 32 pins? Yeah, it's 32. 8 times 4 is 32. So yeah, it's 8 per side. 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we got that's our 8 to make a 328p. We'll label that 8 mega 328p B hyphen AU. Okay. And from there then, we we can like glue that down, I guess, or whatever. There's a lot of different ways to do this, but this is now on basically like a miniature PCB. There's so many ways to do it. I have options, and I'm not sure how I'm going to do it, but definitely, my idea is that this .01 millimeter piece of copper strip, just bent in half, is the surface on which I'm doing all of my connections to this. And it's going to be interesting to see how I pull this off. But basically, I'm planning to add nickel strips to each tooth of this, running off of this, is the plan anyways. And so each one of these then will run to whatever part they need to go to. So this microcontroller is going to be switching on and off, like, I don't know, like possibly a driver to a MOSFET, or possibly a logic level MOSFET itself. And then that will be here, and like a ground would need to be going to that, and then whatever other wire, like signal and ground, and maybe there's only 2 wires that go out to it. I don't recall. Maybe just ground and signal, I guess. And then you'd have like your component or whatever. And that would be like one little and that could be as long as you want. Like this, I drew it kind of small because I was running out of room, but that could be like out here, because this is zoomed in. So we'd have our little microcontroller right here, and we'd run that out to like however many wires need to be on this would be on this, would run out to our little SMD component, which would be like kind of Deadbug soldered. And all the wires would come off that and just come right back to the microcontroller. And then this could go out to a switch, to a reset switch for the microcontroller. And it could also go out to a so we'll do MOSFET, reset, switch. How about a status indicator? LED. And it's going to need to go out to at least 6 MOSFETs. And it will need to go out to, well, since one microcontroller is going to control 2 different brushless DC motors, which each require 6 MOSFETs, we're talking about 12 MOSFETs will be ran out to here. So that's going to be a lot of stuff coming off this center point. And it will also need to go to a fuse, a resettable fuse. And heck, I'd kind of like it to go off to a potentiometer even. Although, wait, no. For that, since that's kind of a separate deal, you can do this, like, just for your own preference. I don't need to erase that. I could put something else on it. So off the microcontroller, you can run a wire down the base of the tree, and then so you can run down, hugging this main nickel strip. You can run down, over, along the bone, and then up a new tree. Not too far away is the base. And note, these trees can go, off in different directions, because they're bendable. They're just going to go wherever. And off this tree, you can put a potentiometer little dial, which if you turn that dial, it will just cause the microcontroller to start turning this motor. And like I said, all these MOSFETs are to run this motor, so those wires are coming down off the MOSFET, down the base, and over to the motor and into the motor. So all the wiring goes along the bone and then up the tree and then out to the component. And here's the best part, like you can have a million components, however many you can envision in your mind's eye. You could literally have like 400 components coming off this as flower petals. And they literally are like this, like they're just floating in the air. But they're not in the way. What happens when you want to put the skin of the robot on? Because this is flexible and every one of these are completely flexible, you literally just smash this down when you put the arm back on. And you can literally just move it to the side like blades of grass. You can take your hands and just bend them out of the way and tuck them down, and like literally they'll stay down, and then you can work on like sewing or detaching a motor and replacing a motor. And then you could just lift it or lift one back up just to work on one. You just face it at yourself and you'd be like working on it here, and it's in mid-air, like near your face, so you can ergonomically work on it. Like it's literally like 8 inches from my eyes, so I got a nice close-up. It's close to my face, and I'm like working on it, soldering and whatever. And then like when I'm done, I push it down and I can lift up another tree and face me and work on that. And so it's super sick. Like you can access everything, and it's like a little helping hands built in, because it's like right in your face. Everything's just being held up, and it's coming off the robot arm. It's like these growths. It's like that TV show where everyone's got that disease where they're growing mushrooms. The Last of Us. It's like mushroom growth, some kind of gross growth coming off. And here's another kind of cool perk I think might happen is when you go to put on the exoskeleton mesh and the arm silicone, you might not even need an exoskeleton mesh. This might form an exoskeleton mesh. If you just kind of shape all of these in a certain way before you wrap the silicone, like the silicone skin around the arm, it would like keep the silicone skin from like just flattening. It would like keep it kind of puffed up maybe. Although if you hit it with a football, it would like compress down, so like there'd be a permanent dent in the silicone. You'd have to like kind of puff it back up like a pillow. You got to like hit it to like cause it to puff back up. So that could be an issue, unless if you put like you could put a strip of zip tie along this base, which has a great memory. So like once it was bent over, it would like lift itself back up. And that's something you see in grass or dandelions. If you walk through grass, it doesn't just stay pressed down with your footprint. You see it slowly lifting back up. It has a memory. And so if you pictured literal grass growing off the robot bones, that's like electronic component grass. If you put it in the arm, if you press the arm down, it would lift back up. If it was real life like grass from your yard, it would literally, if you press the arm down, it would form a flat spot, but then it would lift back up. So that's how I want it to be. It would like lift back up. So it might be like It's conformable, which is key. So like, it would be pretty much impossible, indestructible to break this. If I take a circuit board, I can break a circuit board. But how do you break a dandelion? You can stomp on it. You can have an elephant step on a dandelion, and it's not going to break it because it's too flexible. This is rigid. If this were like bridging two motors or something, you could like press hard and it'd snap in half and it'd destroy your circuit. But if you're doing like this dandelion style where everything's just got a thin attachment point, this would just, like, before breaking, things would just bend out of the way. Like some part would just tuck between two motors. Like it would just like move to where it needs to move to not break. It would like be self-preserving. It would like protect itself. It would be like AI circuit. It would be like an AI, because this is kind of like a PCB, but totally organic, free-flowing, dead-buggy, and flower-like, and like indestructible. And you don't have to worry when you're building your circuits about where am I going to fit everything. You don't fit everything. You just have everything like this wild forest. It'll be like a jungle of just stuff everywhere. But everything's labeled with literal labels. Like I showed you here, you can have as many labels as you need. And you don't have to worry about where will the labels fit either. Everything's just going to compress down. And when you need to organize it, you just like pull out trees. You read the label. Okay, this is the tree for this. No, I don't need that. It'd be like working through like playing cards, like Magic the Gathering cards, like looking through the cards. You just be flipping them. I just like grab a handful of trees. I'd be like, okay, which one goes to which? No, it's not that one. Or I could follow where the base of the tree connects, and that will be near like what it's running. So, like the tree that runs this motor will be connected somewhere in the vicinity near the motor as a clue, so I can like follow the base of that. Because these are going to be long trees that all kind of get tangled up. I'd just be able to start near the motor, find the nearest tree, and follow that, and then pull it out from the group of like just intertangled trees, just stuff everywhere. I just like kind of shake it, pull it out, and then I'd have it in front of me, and then I can work on that. And I just have like all the little parts just sprawling out everywhere. Now, one big issue I'm sure a lot of people would be concerned with who are electrical engineers is like, what about, this would be like one massive RFI producing crazy machine. Each one of these would act like an antenna. This would like be like a signal jammer robot. If it walks in a room, every electronic device in the room will stop working. Bluetooth will be out, Wi-Fi will be down, every device will start shutting off. Like it would shut itself off. It would be so corrupted if you're not careful. And so what I'm going to actually do is every single wire going out to anything, including all power wires, my plan is to have it be shielded wire. So I'll send out the group of wires individually shielding each wire by wrapping it in okay, so let's just say like you got a power and a ground to LED to keep it simple. The power one and the ground one I'm going to shield individually by hand. So the wire comes out. The first thing we need to do, if it's bare wire after we're done soldering it, whatever, is wrap that wire with, let's say, electrical tape. I'm going to use my nitrile glove on adhesive transfer tape as my electrical tape, because it's very, very well sticking and very flexible and very fine, very thin. It's the thickness of a nitrile glove, and I just think it'll be, I've been using it for a long time already to shield my electrical wiring. Instead of like shrink wrap, I just use this. And so I would wrap each wire with this. Then I would wrap the wire the whole length with this copper tape. I would wrap it. So I'd cut out like a strip and then I'd wrap it. And since I'm thinking my wires I'm going to use are going to be 0.01 millimeter nickel, um, what is it called? Nickel strips or whatever. Um, for welding like lithium batteries together, 18650s. They use this. I'm gonna like use a wire to cut this down in width to like maybe 1.5 or 2 millimeters wide. I'll use electrical shears, I think, to do that, or tin snips. I'll cut thin strips to do all my wires. So it's very, very thin, very, very tiny. It will be like little traces of a PCB, literally. It will be that size. It will be a trace, essentially. It's the same thing, except this is much stronger than copper. So I'll be having like little PCB traces as my as these things coming off. I can make them like 2 millimeters wide and however long I need, like maybe like 3 or 4 inches long, going out to each component. And so I'd be wrapping this. Imagine it, it could be this size too, don't get me wrong, but a lot of them I would prefer to be like maybe 2 or 3 millimeters wide. And I bought a pack of 100 millimeters long, so it's like this long, and it's 4 millimeters wide nickel strips. So I might just use that, or I might cut those in half so it's 2 millimeters wide, and it's 0.01 millimeters thick, but it's very tough. I did tests with this. Like, this is so much stronger than copper. It's so robust. That's why they use it for batteries. It's like indestructible. So I'd wrap it first. Maybe you just fold it in half and then just cut the excess with this. And then I'd wrap it, maybe just fold it in half, cut the excess, the whole length, with this copper foil tape, super thin. And then I need to solder onto the copper foil a ground connection, so it's a grounded shield. And then I'll wrap that with another layer of electrical tape, which in this case it'll be this as my electrical tape. I'll wrap that again, and boom, that'll be taped off. So it's electrical insulation taped first, then it's shielded with copper shielding foil, and then it's electrically insulation wrapped again. So that's, I know, a lot of extra work, a lot of extra steps, but doing that will be the key to completely eliminating all EMC/EMI concerns, which stands for electromagnetic interference. And I think electromagnetic capacitance, I'm not sure, pretty sure. It would eliminate that, because this would be the same way like USB wiring does it. USB wiring will have like all the USB cables going through it, and then it will have like a metal shield around everything, and then it will have and each wire is shielded. Each wire inside a USB cable is shielded with insulation, and then they're all together, but then the outside of it has a metal shield, and then after that is insulation again, like rubber insulation as the outer, and then it goes to the plug. So, and then if you look in like your headset, when my headset broke, you guys know I did this repair on my headset cable. Let me show you that. Remember this, guys? This is my headset cable. You can see how skinny it is at the bottom, and then I cut it in half, and I actually was able to replace it. And you're hearing me on this now. This is my repair. You're hearing me on this headset that I did this on. I'm speaking into this, and you hear no static because I re-shielded it all, and I reconnected all the shielding that was inside it. Now this particular cable did it the way I'm planning to do it even more. It's an audio cable, And so it's even more careful about RFI interference than USB, I think. And it individually does this. Like, there's the signal wire, and that's coded in like a conformal coating of like some type of plastic or rubbery plastic, so it's insulated. And then around that is like tons of very fine threads of metal forming a shield that's like twisted. It's like braided metal. Like if you just took like 50 little hairs and like twisted them up the whole length, it would form like an impenetrable network of metal tightly woven against it that like completely shields that signal wire. And each of those hairs of metal was insulated individually with a lacquer coating. And so everything was electrically insulated and everything was shielded for each little signal wire going through it. And there was like, I want to say like 4 or 5 or something. So to repair it, you had to like take away the insulation from each one on both sides, melt off all the lacquer from each little strand of it and scrape at it with a knife, and then clean that so it's all exposed so it can be soldered. And then you had to twist together both sides of the insulative shielding in order to make it electrically conductive the whole length of the USB again. And then you had to twist together, after melting all the coating off each signal wire, you twisted the signal wire together so that it's now conducting again the whole length. And you had to do that for each wire. Its shielding and its signal wire you had to do that with. And then after that, you had to tape off everything to insulate it. And then you had to like bend all your little twisted pairs over. And then you had to wrap it all in insulation to like seal the deal. And then to make it not like bend at that place, because it's all very delicate what you just did. Oh, you had to solder each thing too. And then after it's all taped down and everything, then since it's delicate, you don't want it to bend there. You have to use like hot glue or some type of caulk or something to create like this bulge along the whole length so that it doesn't bend there. And then after that, I wrapped the entire thing with aluminum tape as the final thing, just to make sure like I'm keeping any electrical bouncing waves and stuff from like going into there easily. So kind of like it would be like a Faraday cage, I guess. And so that's how I did it. And so that type of cable has the same type of ideology of really protecting the signal integrity and not letting electrical interference mess with those cords in there. So it will neither give off nor receive little electrons coming from anything floating through there, or however that works. No electrical waves are going to make it into there. And so in the same way, we don't want electrons coming off this, because it's like a nightmare as far as like, if when I took like some lessons on electromagnetic interference and how to avoid it, like for PCB layout and stuff, this like breaks every rule, and you're like guaranteed to to just be completely destroyed by this. Oh, by the way, the microcontroller in the middle going off to all the MOSFETs here, I don't have to do it that way. I could put the microcontroller on a separate pedal or on a separate flower, like over here. But keeping it on the same flower, I think might be smart, because they said in the EMI booklet, which I don't want to completely ignore for the purpose of the design of these other practical concerns that I've been talking about. I don't want to concern one principle, which is that for very high speed switching, you want to keep the traces as short as possible. So that's why I'm planning to keep it on the same pedal. Because if it had to travel down and then over and then up another tree, that could be an issue. So let me write a little note here. Potentiometer for testing forward / reverse of motor. Okay, so that's actually coming down and then over on the bone and then up to the potentiometer. Now you'll note I don't try to just connect this across. That's the cardinal rule. You can't connect from the potentiometer over to this flower like a clothesline between the two, because then if this tries to go this way and this tries to go this way, that will snap, and no longer can these just interchangeably go any direction when you're just trying to tuck them, bend them. Now there's dependencies from a mechanical point of view that prevent the blades of grass from being parted any which way. What if I wanted to get down to here to do some repair or add something new, but this wire between these two prevents me from pulling them apart to get down at the base of it and work on something? I want access to everything at all times and nothing to ever be denied access to. I need access. So like you'll note also the base of this little electrical tree is not too near to the motor, because if it was, I wouldn't be able to get in here and suture on a new motor if I needed to replace this motor or the pulleys or something like that for repairs. I sew on the motor after wrapping it in cloth. I sew at the base, sewing it to the bone, which is also wrapped in cloth. The motor is specifically wrapped in football jersey mesh so it can still breathe. And inside the football jersey mesh is anti-skid rug anti-skid paste so that it doesn't slip around so the motor can't spin inside it. You want the motor's output to spin, but not the motor casing to spin. It's not an outboard motor. So you want it to be stationary. So it will be sewn in that way, but still be able to breathe. That's why I didn't use solid cloth. I used football jersey mesh because it has the little holes in it so it can breathe. Practice jersey mesh specifically because it's got bigger holes. And by the way, out of each hole, I'm going to send little copper solder wick braids, a bunch of them coming out that are wrapped around this motor and attached to the motor with thermal compound, which is going to... copper is a fantastic thermal conductor, so that will draw heat away from the motor, and then with all these little braids sticking in the air, the motor will have like a little afro. And air blowing across that would blow through these little braids, acting like a radiator fins. And that would then cool the motor. And we talked about that in my cooling series, but I'm just mentioning some things, review. So, and then for those the afro hairs coming off the motor that act as cooling fins, not only will air cool them, but they will also wrap around a copper tube or copper pipe tube, like refrigerator line copper tube, that happens to be passing through and then running back to the cooling system inside the chest of the robot, but it passes through the whole arm. And it goes from copper tube to rubber tube back to copper tube. When it needs to make bends, it's rubber, so the copper tube won't bend and bend. I'll have rubber intersections for that, like vinyl tubing, for any bends that it needs to make. But then it'll go back to copper for the purpose of letting any type of solder wick braids coming off of a motor will then wrap around the copper tube, and water will be flowing slowly through the copper tube in a circuit and then back to a pump. And actually the water will go into the artificial lungs, trickle through a mesh, where the lungs are opening and closing, and air is being pumped through them, like a like under pressure, like how lungs work. And so like the things for a chimney, where you got the handles and it's blowing out and sucking in when you open it, or that's what they used to like stoke a fire inside homes in the old school days, kind of that principle. So the water cooling will trickle through a mesh inside the lungs, and that air that's being exchanged by the lungs will pass through and against all the little water that's spread out in this mesh. So it's like spread out, and the air passes through the water, maximizing the surface area contact with the water. And this will do the same thing as evaporative air conditioners. The same principle, working principle. The evaporation of that warm water hitting that air passing through it creates evaporative cooling. And so that cools the water. As the robot's breathing, it will also, not only will the air that it's breathing be sent out of the lungs and through the various cavities of the body through tubes, and then exhaust tubes will exhaust out the nose of the robot. From the whole body will have exhaust tubes running through it and exiting through the nose. But also through the nose of the robot, it will breathe in new air from outside the room, because the whole robot's like one big rubber suit, and so all the heat's trapped otherwise. Air will be exchanged through the nose, and that will then bring cool air in. That will cause the evaporative cooling of the liquid cooling system I just described. And so that's acting as an internal air conditioner inside the robot. And so it's got air cooling and liquid cooling systems for the whole robot. And also, he'll be able to swallow a whole bunch of ice cubes, or even ice water, and that will form the liquid cooling. When his onboard liquid cooling gets to a certain temperature, he'll pee it out in the bathroom and then drink ice water to replace his cooling water with cold water. And that will remove heat from the body that way. When cold water turns to hot water, that takes a lot of heat to do it. Think of how long it takes for water to boil. It takes a ton of energy and heat to cause water to boil. Water has an insane ability to just take on heat into itself, and it slowly gets warmer over time. And so it will be able to just, we'll call it tank, like an MO. It will be tanking a lot of that heat itself, and the air cooling will be bonus. And it will help to keep the water cool as well through that evaporative cooling system I mentioned. And so the ice cubes, if it drinks ice cubes and ice water, will be like a storage mechanism for anti-heat. So all the heat being produced in the robot is going against us, and all the ice cubes will be anti that, buying us time. So think of the ice cubes as like batteries that have a certain amount of heat counteracting power. And so if you drink a big gulpy or slushy, although I don't want that stuff gumming him up, it has to be just water and ice, that will give the robot a lot of heat countering power, quote unquote, to fight against the heat it's producing for a long time. And he'll definitely need that if he's like mowing the lawn on a hot day. I mean, think of if you yourself put on a dry suit for kayaking and then mowed your lawn on 100-degree weather in the sun, and all that heat is trapped, you'd be sweating bullets. You'd be soaked, so overheated, trying to cool yourself. And the robot, I chose not to have him sweating internally because of the electronics, but I may have him sweat externally. I may have him sweat externally. But I'm not sure how much that will help, since that's outside of the danger zone, which is inside the robot's skin, is where everything's getting hot. So I don't know how much external sweat would help on that. And it may not be necessary, but it's something I keep in mind anyways. It could help, maybe. Because I bet that silicone skin would get hot too. And if he's got water cascading down that, and then the wind outside is blowing against that water, that will create a lot of evaporative cooling of the silicone skin, which then would be removing some of the heat of the overall robot. Since if that skin cools off, there's a lot of that skin, the whole body of the robot has skin, that's removing a lot of heat much quicker. And so the heated air inside the robot, which, you know, it's working through expelling that each time it breathes, whatever. That air won't have warm or hot skin around it, adding to the problem. If that skin is getting cooled off, then the air, which transfers some degree of heat to that skin, is going to be cooling down as well. So there will be some degree of heat leaving the system just by having external sweating. So I think even if you were to hose down the robot, that would cool it off too. And you could do that because that wouldn't harm the robot, because the whole robot is in a silicone skin suit. You could actually hose it down with a hose, and that would help it cool down. In fact, if it were wearing clothes, which it has to be, because it's a humanoid form factor, it has to wear clothing then, you could just spray it down with a hose, or it could spray itself down with a hose, and it would be just soaking wet outside while it's mowing. All of its clothing stuck to its body, and then as the wind blows outside, that would cool it a lot. So that's another thing to bear in mind. He could even have a spray bottle with him full of ice water and be spraying his face and arms and stuff with that, the same way a human would to cool off. Ice water spray bottle. So there are many ways we can get that. Instead of sweating, maybe he'd do that. But it'd be kind of cool, I think, to have little tubes that exit the skin at certain key spots, like the armpits and stuff, that send out a trickle of water, which soak his armpits. So he would have like wet armpits and wet butt. His underwear would be wet. Maybe some could come out his forehead, and he'd have kind of some sweat drops dripping down his face as he gets hot. Internally, he would start opening up valves to start sending sweat down. Some solenoid valves or whatever would open up this, and he'd begin to sweat when he felt the need to. So that kind of stuff is super cool. Anyways, yeah, I'm definitely nerding out. I just had well, I shouldn't say that. I was gonna say nerdgasm, but I don't think that's appropriate. So anyways, so I apologize. Okay, so basically, oh, and then, okay, so like these MOSFETs, after we get it completely thermal or electrically insulated and shielded and everything, all the wires going out to it, I wanted to put some thermal compound on the top of the MOSFET and then stick copper braid, solder wicking copper braid onto the thermal compound, and then wrap all that in electrical tape. And then we've got to wrap, because that's so close, I feel, to a MOSFET with the switching, it might have some type of electrical capacitive. They said if like something's close to something, like if you put a heat sink above a chip and you have other like a lot of traces running under that heat sink, there can be an electrical capacitive connection where, like, I guess basically electrons are jumping off parts and hooking themselves somehow. Magnetic waves are like attaching to that heat sink, and that heat sink itself becomes an antenna, and it can couple with something with an opposite charge across the way somewhere, like a cord or whatever, and that would actually form an antenna, which would then give off RFI signals and basically disrupt surrounding electronics with like sending actual signal pulses. It could mess up your Wi-Fi or whatever. It could cause electrical devices to malfunction because it's offering electrical magnetic interference. Alright, quick editor's note for the braids coming off the motors for the cooling. I think those just have to be tied to ground, so I have to make sure chassis ground attaches to those so that they don't become any type of antenna. And then wrap that on the cooling pipe, the water cooling pipe. So that way heat would be drawn through thermal conductivity from the motor to the water cooling pipe, but it would also be able to escape through convection, which is where the heat waves just kind of, the air blowing against it just carries it away. So, no, I think that's not evaporative cooling. That's convective cooling. So that would be two different ways it's cooling off the motor. And as I said, for the MOSFETs that control the motor, those would have thermal paste and then the same thing, solder wick braid, because copper is a great thermal conductor. So in other words, heat travels through it just like electric travels through it, and it carries that heat. I learned that the hard way. If you hold solder wick braid and you stick your soldering iron against it and try to like, you hold it for a while and it's trying to suck up the solder, your fingers get burned even though they're like 4 inches away. Like literally within 1 second your finger's burning and it's cooling off your soldering iron tip quickly, because that heat is traveling up the braid and onto your hand and burning you. So I was like, whoa, solder wicking braid has amazing thermal wicking capability that wicks heat away from a heat source. So that's why I was like, that would be great to wrap around a motor to draw heat away from a motor, and then it would act like radiator fins that the air can then blow across and cool the motor even more. Basically a afro coming off the motor, that each hair of the afro draws heat away. I mean, you guys have seen if you guys build your own computers, you put a heat sink on your processor, and that basically is like a flush connection with thermal paste to the top of the processor, and then the little fins of the heat sink stick up, and the air blows onto that. You actually put a fan on top of that, and it blows air across these fins, and that causes the heat to go onto the epoxy of the IC, and then the heat travels right into the thermal paste, then right onto the aluminum heat sink plate, and then up the aluminum fins, and then the air blows onto the fins as the fan blows, and that transfers the heat to the air, and then the air blows out the side of the computer. And so the same principle I'm using to cool off the motors of the robot with my little solder wick braid fins, except I can't put a physical big heat sink because that would take up space that we need. We are the most Scrooge McDuck space hoarders for the robot possible, because you need thousands of components just in the robot's arm, or millions. Maybe not a million, maybe like 50,000 things are going to be on here. You got stuff everywhere. That's why I have to get insanely creative about how it all fits. And so by having it be solder wicking braid just coming off, that's like 6 inches long for each one, when then you try to put the skin of the arm on, they'll just all bend out of the way. They'll make room because it's all going to be like a scrunchy, like you know those Brillo pads or something, like you can like squeeze it, like it will scrunch down because it's all just like little hairs. Like if you have like an afro, people have hair like this big, like some guy on like a cartoon with a huge afro. Like some people have huge afros. They can take like a rag and like press it all down and then like make their head look small, like a do-rag. They can do that. The same principle applies to my electronics. I can put a huge do-rag over all my electronics and it will all compact down. But then when I want to work on it, I take the do-rag off and I use like a pick. Maybe I should use a real afro pick, literally. I might. And I use the afro pick to like lift up all my electronics to a big afro, and now I can like see everything and do repairs and stuff. And then when I'm done, I just scrunch it back down, just like an afro going down to a head, and now it fits. So that's how everything is designed. The design principle's there. The only stuff that can't do that is like the motor, because it's got a hard shell. But everything that doesn't have a hard shell, you can scrunch down. That's why all these wires and stuff coming out are able to scrunch back down. So everything's shielded Otherwise, this would be insane, like the amount of antennas that would cause, and that would be an electrical interference nightmare. No signal could ever get to the microcontroller without being so corrupted that the microcontroller can have no idea what it's saying. Like, you could use CAN, I2C, your own custom protocol, bit banging, whatever you do, it would be so corrupted it would be hard to make it out. So it would ruin communications and cause unexpected behavior. But because we're planning to hand shield everything, we should be good to go. And actually, like I said, I was planning to shield it with this type of tape, but now that I'm thinking about it a little more, I might buy some MG Chemicals graphite conductive shielding paint and paint it. I need to see what the dry time is on this, because this would be instant. It's just tape, you just wrap it. But I might paint it, because that would be great shielding too. And the conductivity doesn't need to be that high for shielding. It just needs to be okay. It's just meant to stop electrons from just... I picture it that way. I mean, I might not be saying it the right way for like some engineer, but I just picture like electrons just like floating through the air, and think of it like corona masks. Like, if you paint all this stuff with shielding, that's like wearing a corona mask to stop virus particles from entering when you breathe. And so electrons are like the virus particles, and you don't want other machines and like your Wi-Fi router, your Bluetooth, or your phone, or even just stuff giving off a lot of electrons from poorly designed electronics in your house. You don't want those electrons shooting around your house to enter into these antennas and then get into your electronics. Now that's like stray electrons traveling through your wiring. That's going to start messing up stuff and changing voltages and just like your wire. So I might go that route if it dries really fast. I mean, that could be pretty awesome. Shoot, I could just take like a heat gun and just blow it against there, and it would just like quickly get dry to the touch. That might be quicker just to paint everything. As long as you make sure to paint like the whole thing, that could be good. I mean, so maybe then, I mean, shoot. Even if you just use regular jumper wire, then you could just you could like dip your jumper wire in paint before you start, maybe. So it would all be like shielded before you even begin working with it. It's already shielded. You would just have to make sure to attach a ground wire to that. Oh, that would be a problem though. If you want it shielded and the shield grounded, you'd have to connect a ground wire. So you would need to well, I guess you could like send a wire off and then like just wrap it a couple times. Yeah, wire wrapping. You could just wrap it. The ground wire, just wrap it onto the paint and put a little more paint on. Wire wrapping. So that would work. Cool. So we wouldn't have to worry about trying to solder to the paint. Just wire wrap it real snug, and that would be enough with a bare wire. I have wire wrapping wire too I could use for that. In fact, wire wrapping wire would probably be perfect for a lot of this. That stuff is fine. Let me show you guys wire wrapping wire. It's pretty wild stuff. It's pretty fine. Let's see. What gauge is it? It's 24 or wait. Why does it say AWG 24/30, 26/28? It's like giving options. I don't know what. This might be 30 gauge. Look how fine this is. This is like the stuff in like a network cable. This is tiny. This might be the kind of wire we should use maybe to solder all our like tiny SMD. Like if I needed a SMD capacitor, maybe I like solder this to a leg of it, or even solder it to an IC chip. And like oh, this is the other thing. Once you solder this onto like the leg of an IC, you're like, well, that'll just break so easily, right? So like you would want to like fold it over and like glue it to the IC. So like you guys know how like let's say like this were soldered to my finger. You would want to like have a loose loop and like glue this to my knuckle or tape it down. So then like when you tug on this now, it doesn't tug on the soldered joint because it's like tied down here. What do you call that in electronics? There's a name for it. I'm drawing a blank right now, but like it's like mechanically protecting your wires from being tugged on by like pinning them down somewhere. Um, and so for that type of thing on this tiny scale, like pinning down stuff or whatever, safety reinforcement, yeah, something like that. That's not the word, but that's a principle. Um, for that, I had the funniest idea. So like, I became a prepper a couple years ago. A lot of people became preppers during Corona, and I bought everything to do like DIY dental if the world fell apart. So I have like a dental drill and stuff, and I bought filling material, dental fillings, and I can use this as like the glue to glue down like wires to like if you have a bunch of these little delicate wires coming out of the IC, you use fillings. I would use fillings. This is light cure composites, nano composites. This comes in like a tube, and the same thing you'd use to fill in a tooth. It's got to be strong if it's for your teeth. And you can actually see, you can open it up, and yeah, you can actually see it. That white stuff in there, that's for tooth. So I would like take a little scoop of that and put it on the wires and like glue the wire joints over the solder joints with like some space to spare, like kind of spackling it down the sides of the wire, and then I'd take a UV curing light, which is in this bag too, and I'd cure it, and it'd be as strong as a tooth. And so you wouldn't be able to just rip that wire off the IC anymore because it would all be mechanically bonded. And I could like put that around like the entire IC or just around the wire connections and like glue it to the side of the IC. I had a feeling this small scale dental stuff would help. So like these little you see like it's got like a little spoon shape, tiny on the ends of these metal tips. That's for like pushing the filling into the tooth and stuff. And this is actually made for like scooping up the filling material. There's like little spoons you can picture if you can't see it on camera that well. And I would be able to scoop a little bit of that and like put it very delicately like in certain spots, or like to glue down a component just to keep it still on a little PCB before I like start soldering to it, like a SMD component. So I feel like this is going to help a lot for different little stuff like that. I'm going to be using those techniques. And I think that's a good segue to take you guys into the next group of kind of big developments on actually how I'm going to be doing this. Like, I call this a Deadbug style, even though it's like a living bug style, because the IC is not necessarily going to be flipped upside down. It'll still be flipped downward, but we're going to be soldering to it. But it's still like the Deadbug. I mean, it's bug-like. I mean, heck, this kind of looks like a water spider. If this is the body of the spider and these are little pads on the water, it looks like a water spider at the top of a blade of grass just sitting there. That's how it's going to look. Do I want to say any more comments? So basically, we can have as many of these like flower-like electrical circuits that we want. Every one of these will be scrunchy, and you'll be able to press it down. This will all bend, and this will all just go wherever it needs to go. And it's indestructible, I feel like, in some regard. It's like you can fit like 50 of these in the arm and just scrunch them all down. They won't take up any space because it's just loose wire everywhere. If I took a big rat's nest of loose wire with tiny little SMD components at the end of it, you'd just be able to ball it up into a tiny little ball. Whereas like if you put that on a layout of PCB, it'd take up a huge PCB with all the traces and everything spread out. So this is like if you took, okay, this is what it is. It's like if you took a PCB and you could like use the wand tool in Photoshop to select the fiberglass board, and that got selected, and then you press delete. And now you're just left with all the components and all the copper traces left. And then you just scrunch that into a ball, but it's all thermally insulated, so it doesn't like arc and like cause short circuits, because everything's individually wrapped in thermal insulation. You scrunch it all into a tight ball, and you could like make a little tiny ball of a huge PCB. So you could literally like just scrunch all these up and just tuck them somewhere out of the way when you want to close up the robot when you're not working on it. And then when you need to work on it, you just pull something out of the ball and spread it out, and you can see it all, and it's got labels and everything. It's going to be insane for like doing repairs and stuff and troubleshooting. Oh, and I also thought of this. So like I could assign a little LED to each MOSFET so that when a MOSFET turns on, the LED turns on. This is going to freak you guys out. Like a little blue LED assigned to each MOSFET. And so like as the motor is switching, these little LEDs flash. And that indicates actually for troubleshooting what order the LEDs are hitting at and which LEDs are flashing, which are not. And you'd have then a bunch of LEDs at the tips of this like flower. It would look like something in like a sci-fi movie, like with like little lights on the. This would look like Data on Star Trek's or something, like little tiny LEDs on the tips of all these things on a flower. Look beautiful. It'd be like a black flower with little blue tips on each flower petal. It's gonna look like sci-fi. In fact, you see how the flower just goes on a horizontal plane in my drawing? We could have it create a ball, and it would look more like those dandelions that are like the seeding type that you can pick from your yard and then blow on them, and it sends the little flying floaty things. It would look like one of those, but like a super cool steampunk version that's got like a little light on the tip of each little thing, and they can't blow away. And so there's going to be no she loves me not. That would destroy the circuit. Unless if we had them detachable, then we could she loves me not. If we created a little detachable thing at the base of each one, maybe that would be smart for even more robustness. Because that way, even if, God forbid, a football hit the robot in the arm so hard, it would have ripped off one of these little wires from the flower. It would rip off at a detachable joint. You'd be able to open the robot up, find out what happened. You'd see a flower petal missing with like a little stub with a connector. You'd be able to find it, pick it up, and plug it back in. That'd make it modular. Everything would be plug and play. You just have tiny little connectors. That might be a cool idea. You can then tape off the connector, but it'd still be there. So you'd like electrical tape it. But then you'd be able to like reconnect things easily to make repairs if something tore apart. So nothing would be, it would really be indestructible then, because like if something broke, you just reattach it rather than like it actually broke. Wow, that might be best. A cable management hellhole? No, it won't at all. Like I said, the cable management, the flower, everything just converges down the stem or the stem slash the trunk of the tree, and then it forms a nice loom that runs along the robot's bones. You would just have your bus wires, like your main power wires, that just go up along the bones, tight to the arm. And so those are like the roots of the flower. So there would be root systems that go out, and then those root systems then come up and form other flowers. So it would all be really nice. There would be no desire to make the flower go away. The flower is the circuit board. So we want the flower to just be a flower, and you can just move it out of the way, like parting grass. And then when you're done, you just crunch it up. You never are going to wrap this thing into like a loom or wiring harness and have it disappear. The flower needs to exist. It needs to be able to be pulled out and looked at without undoing a whole bunch of tape and stuff. When you open the robot up, you can just see these flowers and pull them out and spread out their petals and like just look at it and troubleshoot it. So you don't want flower to flower connections or treetop to treetop. You don't want clotheslines like between two windows of a building. If you could picture them as buildings, you don't want to do any clotheslines. They all need to be able to be separated so you can get down there and work at the base of these flowers. So this way there is no need to schematically figure out where do I put my components, where do I fit this board. Like if I bought an ESC, right, to run one motor, let's say it's like this big, I'm putting 25 motors in the arm. Where am I going to fit this ESC? Do I put it here? Do I strap it here? How do I bolt it on? I don't need to worry about any of that because my ESC is a flower. And I can have as many flowers as I want, and they take up literally zero room because they're just floating, and they can just be scrunched up like afro hair and just tucked in against the robot, and they can be lifted up and then moved out of the way like hair on a head, and you can work at the scalp of the robot. So it's not a cable management hellhole. It's actually cable management dream. It's a cable management paradise or heaven. This is cable management heaven, not hell. Heaven. Okay. So yeah, we'd be able to put blue LEDs underneath the MOSFETs, and then a red status indicator LED, and a resettable fuse. So the fuse would blow if anything short-circuited, instead of like burning up a battery and having a pop and magic smoke. We'd never have magic smoke. We'd have fuses everywhere. To not be lazy, like most people don't use them except if you're a professional, but as a hobbyist you're probably, I don't need a fuse. I bought a ton of fuses. I should use a fuse for every single motor, because if these motors stall out under load, like the robot's trying its hardest to pick up something it can barely pick up and it's struggling, it's like got a rock in its hand, it's trying to lift it, or a dumbbell or something, and it's like burning up a motor, right? We got so much cooling, the motors will be able to take a lot of that quote-unquote burning up because they won't burn too easily. They're so well cooled. But eventually, the heat will ramp up through time, and it will be at its full strain. And maybe the circuitry will be struggling to handle the amount of current that motor's asking for. And it might want to burn out a MOSFET. It might exceed the specs of that MOSFET's amp specs. And that MOSFET's maybe eventually going to overheat, even though each individual MOSFET we're going to be running a heat pipe off of to a liquid cooling. So each MOSFET's liquid cooled. Individual MOSFETs are liquid cooled. People liquid cool a ESC, but my ESC is a flower with each individual component that needs to be liquid cooled being liquid cooled. That's next level. And by the way, the liquid cooling would be the solder wick braid. It would run down the base of down the flower petal to the stamen, down the stem of the flower, over to the arm, and then up to make its own flower. And it'd be like maybe 7 inches long or 8 inches long, just stubbed out until I put in my water cooling, and then I'd wrap it around the water cooling pipe with some thermal compound against it, and I just wrap it up and then tape it down or whatever, and it would then be able to send the heat from the MOSFET down the stamen, down the stem, over across the bone, up a new flower or blade of grass. I call it a blade of grass if it's just got one thing, so in this case it'd be a blade of grass instead of a flower. Flowers are more complex circuits, so it'd just be a blade of grass, and then that would already be probably enough cooling for this MOSFET, even if we never connected that to the actual liquid cooling. But by connecting it to the liquid cooling pipe, now you've got an extra just radiative fin randomly coming off the robot in general, that the warm air in the general region will be hitting that fin and warming that fin.
And that fin, which is then connected to the water cooling pipe, would then be taking some of that warmth out of the air and into the water cooling pipe. So the more random wires you've got wrapped just anywhere passing through the air in this compartment, and then tacking onto the water cooling pipe, the more that water cooling pipe interfaces with, by maximum surface area, the air in the chamber. So think of like a radiator for a car. It's got the tubes running back and forth of water, and then it's got little fins going up and down, touching the tubes. It's got tons of fins. You know, the ones you bend if you press it on your air conditioner? Each fin is more surface area for air to cool the air passing through it. So the air passes through the fins. The heat from the air goes into the fin, up the fin, onto the cooling tube, and then the cooling tube then gets that heat transferred into or out of it, depending on if it's an evaporative cooling tube or if it's a condenser. Evaporator or condenser depends if it's trying to get rid of heat or add heat, or get heat into it, or however that, yeah, heat either entering or leaving, depending on which it's for. You want a lot of fins. So each cable, each solder wick braid I run from a component and into that is benefiting us. And I guess it doesn't have to be solder wick braid either. For the motors, maybe, yes, but maybe for the MOSFETs, it could just be a regular jumper wire or something. Because anything copper wire would work. Okay, so what else do I need to say? Yes, this is less overwhelming now. Like I feel like this is like going to be so easy to work on each component, just in the air like this. I feel like you can label each little with a little paper label. You can label each one of these little flower petals, and you'll know everything going on. You'll have little lights that give you a lot of clues of what's going on. If one of these flowers, all the lights coming off of it that correspond to MOSFETs that are supposed to be switching on, you'd see the lights, you know that MOSFET's working. If you have a MOSFET that burned out, there'd be no more light working on it. So you would know something went wrong. It'll just be great for troubleshooting to have a lot of little LED lights involved somehow. So yeah, instead of having like Arduino Nano or something, or Arduino Mini, we're going to have an Arduino flower that we make. Everything's got to be a flower now. Because of the reasons I said. We don't have space to have actual PCBs. They're too big. Even the smallest PCB is too big. Because we need to save room. And this creates infinite room. It's like, now instead of circuit boards taking up too much room, circuit boards take up no room at all. Literally at all. Like, these are like hairs. Look at the wires. These are like little hairs that can be just scrunched down. Like, now it's just air. It's like ridiculous.